Hi everybody. I am Emanuele Faranda. I work at n2n, which is a software company which produces network monitoring software, but not only. It also produces kernel drivers to accelerate the packet capture and many other things. But we won't talk about this in this talk. So I'm introducing this n2n, which is a software which we have developed in collaboration with other people, and now it's a community project. We will see how to use n2n to create network overlays to make the IoT device talk together. So IoT is a big world. Today there are a lot of IoT devices in our homes. I saw the advertisement of Alexa, for example, which is also shipped in Italy. So we can say that also that a lot of IoT devices will come to our homes in the next years. So what are the challenges of these IoT devices? The problem is that they are very constrained environments. This is not always true, but they usually have a limited memory or CPU resources. We need a way to reach these devices once they are deployed to the home. For example, if a new kernel is released, which patches security vulnerabilities, we need a way to reach the device and to update it. We cannot forget this device. We cannot deploy them and throw in the wild. We have to support these devices. This is a critical thing we should consider, because today we have seen a lot of attacks of denial of service, which was performed by the means of IoT devices. We also have other needs. For example, to export data and metrics for this device, and to troubleshoot, maybe to connect to the device for configuration if a customer has a special need. But there are also more advanced challenges. For example, many IoT devices, it is interesting for IoT devices to be internet connected one each other. So maybe they can fulfill a common task in a distributed way. So this is something we should care. Another important thing is that sometimes we need to monitor the device traffic. For example, to identify if there are ongoing threats or possible malicious connections to analyze. And it should be a good way to do this would be to apply policies on these devices. So maybe we can say this device can talk to another only with this particular protocol. So these are some ideas. The problem is that with the internet is a dynamic environment. So we have this constraint which limits our way to reach the devices. For example, the IP address is dynamic, or the IoT devices, once they are deployed to the final site, they are behind a NAT device which hides the IP address. And IPv6 can partially solve these problems, because if with IPv6, any device could have its own IP address, but the problem is that in many cases we need a way to define our own networks and to set up administration policies on them. So this is a typical solution. A simple IoT device is a IP cam which is located at our home, and we try to access the IP camera from the world, so anywhere in the world. The problem is that the IP camera is connected to our local network, and there is a NAT and a firewall which prevents our device from reaching the IP camera. The typical solution to this is to to set up, to open a port on the firewall and to set up, for example, IP forwarding. The problem is that, in this way, we expose the camera and potentially our network to external threats because we are giving the other people a way to get into the network. A common problem with this, for example, many devices use the UPnP protocol. This protocol allows the device to open automatically a port on the router, and this is even more dangerous because we are not aware of this, and maybe default credentials are used, and our devices can get easily compromised. Another solution is to use the cloud services. With cloud services, maybe we can connect to the device via the vendor cloud, but in this way we lose all the, we do not own the device anymore, and we do not know which security features the vendor provides. Moreover, the vendor must implement into their applications, they have to implement all the security features needed to provide an encrypted connection, and this must be done for every product. When looking at the possibilities, there are many VPN software out there. The problem is that many of these are complex solutions. They require a complex configuration, or they are too resources and intensive. And we do not have to forget that many IoT protocols, for example, MQTT and HTTP, are designed to be plain text. So if we try to move the encryption from the application layer to the network layer, we can also reuse these protocols. We do not have to change these protocols. So in our opinion, the IP protocol should be used to carry the information as a transport. So we can use the internet to interconnect all the devices, but we do not have to rely on the IP protocol to reach the devices. We want a way to create our own networks and to manage them. And we want to, as I said, we want to move the encryption from the application layer to the network layer. So we will have a set of virtual networks, and they are encrypted by default. So from these necessities, we have developed, and with other support, we have developed n2n, which is layer 2 VPN software. Layer 2 means that you will have the Ethernet headers on the packets, so you can build any Ethernet-based application on the top of it. You are not limited to the IP protocol. And n2n can cross the NAT devices and firewall devices. So no matter how many NAT and firewall devices are between you and the other device, you can connect to it directly. And it is decentralized. It means that you can create your own network. You can create, you can build many supernodes, which we will see later, which are the fundamentals of this network. And you can, in this way, you get no single point of failure. So this is a pro. Another important thing is that you can join multiple virtual networks together. We call a virtual network a community. So in our vision, we think a user might join a community, for example, sport friends or university friends, and they can share all the information they want within the same community. And they can join multiple communities at the same time. So by the way, n2n is open source. There is the code is all available on GitHub, and yeah, you can review it if you want. So it's a simple code base. It's not complex. It is very easy to set up a working connection, and I'll show you how to. So with a little demo. And it is also easy to integrate it into an application. For example, we will see how to include the n2n library into a C program and how to get the network functionalities thanks to a single function call. And most importantly, thanks to the community support we got, we was able to port the code to many different platforms. So we can, this actually runs on Android, on Linux, on BSD systems, on macOS, and on Windows. So there are already applications which use n2n on this, on all this platform. So this is the main architecture of n2n. We have the edge nodes, which are basically our clients of the connection. And then we have the super nodes. The edge nodes can talk together by the means of a super node, or they can even talk directly if they can. So we use different techniques, for example, UDP hole punching, to establish the direct communication between two edge nodes. So dynamically, if they can talk directly, they will use the direct connection. This means that the traffic will go straight from one edge node to the other with no latency, additional latency. If this is not possible, the edge will go through a supernode. We will tunnel all the supernode traffic. As I said before, edge nodes belong to communities. So we can have many communities in this scheme, and only the edge node belonging to the same community can talk together. So we also have said these things, and yeah, the important thing is that when you join a community, a virtual network, a virtual device will appear on your system. We use the TAP adapters, which are layer 2 adapters. So when you join a community, you will see a virtual network interface in your system, and you can assign an IP address on it. You can apply routing policies on it. You can use the existing system facilities to do this. And so we decided not to reinvent all the things because it was pointless. We already used existing technologies. And we also used the peer-to-peer approach of this because we think peer-to-peer was changing a breaking solution to the network reachability problem. So you identify the resources regardless of their dynamic IP address on the internet. And you also can set up DHCP and DNS servers on this network. So you can basically get a dynamic IP address and name server up and running with no problem because we are just using a virtual network with a standard network address. So as I said, peer-to-peer has been a changing technology. And the most important thing is that it allows decentralized access to the data. In this case, what does it mean is that the edge node can collaborate and they can talk each other in this dynamic infrastructure, and you can set up your own network as you want. So we will see how to do this. There are two main modes to install our software, which is to download the packages from our repository. We provide pre-built binaries. And then after you set up the repository, you can just install the software with the tool of your distribution. Or you can download it from GitHub and then install, you can compile it with make and then use it. Running n2n, as I said, is really easy. So we only need to specify some parameters. So we have to specify the network interface to create. So this is the name of the virtual network interface that will be created. This is the name of the community your device will belong to. And this is the key to your community. So when a packet, when my node will get into a community, it will announce itself through the supernode to all the other nodes. Then if I send a packet to another node, this packet is encrypted. The supernode cannot decrypt this packet because there are two headers in the packet. The first one is the supernode header, which the supernode can interpret. It just tells him that it has a community to forward. And the other part of the packet is the actual data, which is encrypted with this key. Then you specify the IP address, or you can specify DHCP if you want to, if you have a running DHCP server. And then you can specify the supernode or list of supernodes to use for the connection. So as long as two devices use the same list of supernodes and they belong to the same community using the same key, they can talk together. After doing these commands, one on the first device and the other on the other device, you can now ping the initial device, the edge one, from the second device. So I'll show you a little demo. So I'll explain the parameters of this. And so this is a Raspberry device I have on a remote host. And this is my own computer. I'm specifying the same community, the same key, and the same supernode. Here I have address point 1. Here I have address point 10. Then I can launch the command on both the devices. Now, if I open another terminal here, I can ping the Raspberry device. And now, if we inspect the network interfaces on my local PC, I can see a virtual interface, which is n2n test. This interface has been created thanks to this program. If I stop the program, the network interface will be deleted. And here you can see the MAC address, which is generated automatically in this case, but you can set your own. And yeah, this is a virtual interface. I can use the IP tables to filter the traffic on it. I can use TC to shape the traffic. You can route all your traffic through this interface. It's a standard interface. On the Raspberry, we can see a similar interface. Now I can run many of these programs, and each one will get a separate network interface, so we can belong to multiple networks. And so with the code base today, you can set up your own supernodes. You can create your own networks and manage them as you wish. Users can join multiple communities at once. And as I said, if the two nodes are in a network setup, it depends on the NAT type, for example. If they can actually communicate together, they will bypass the supernode for talking. This is also possible in one direction. For example, it is possible that a packet from host A to host B goes through the supernode, but the response packet goes directly to B, from B to A. So it depends on the network type. As I said before, it is also possible to integrate n2n as a C program, as a C library. You have to define these network parameters, and then you can call this function edge init. And with this simple function, you will create a virtual network and you will join it. So as long as you specify the supernode address, you can join this with a simple call. We have already integrated n2n into a final user program. We have integrated it into n2n. n2n is a monitoring tool, and sometimes we have the necessity to access the user, to reach the user machine, because this does not give us the access, for example, the SSH access to the machine. It just put my machine and the client machine into the same network so that we can connect to the n2n GUI, for example. So with this configuration, the user can enable remote assistance, can download a script, a connection script to send us for the connection. It can also enable a GUI temporary access with a password which is derived from the credential here. But this is a community project, and n2n is also a community project. So the users can also set up their own supernodes. This is our supernode, but if a user wants assistance from another user, then they do not trust us for some reason, they can use their own supernode here. So let's talk about performance. Performance is really a delicate task in this case, because I can say that we are working on it in order to improve the encryption performance. Because here is an example. We have a line rate of 1 gigabit. I'm testing it with the SSH copy. And we have a direct transfer of now 100 megabits. If we use n2n without encryption, which means if we do not add the -k option, then we reach 850 megabits, which is a good result. The problem is that if we enable encryption, actually we only reach 1/8 of the actual rate. And this is bad. This happens because we have privileged the portability over the speed. So we use some bundle libraries. And if we move the support from these bundle libraries to standard libraries, which are deployed via the system packages, then we can improve this speed a lot. This also is really, encryption here is really CPU intensive. So it really depends on your hardware. So on a Raspberry, this number will be pretty low. But yeah, it is a work in progress. These are some ideas we are thinking about for the next release. For example, we would like, right now, if two hosts are into the same community, they can talk together. They are into the same network. So if I send a packet to an host, another host on the same community, potentially it can intercept my packet and decode it, because the encryption is a community group. So there is not end-to-end actually encryption. But if we can provide asymmetric keys for an host-to-host communication, this would increase the possibilities. We want also to leverage hardware encryption, as I said before, to increase the encryption speed. And yeah, because now it's really bad. Okay. Then another important thing we look at is the possibility to make it stealth to DPI software. Right now, as I said, the main header of the packet is clear text. So potentially a DPI software could intercept it and can just drop the communication. But for example, if we define a key, which is a pre-shared key between all the edge node and the supernode, we can encrypt also the header. So this, we can make it stealth to DPI software. And another important idea is the possibility to inspect the network traffic directly on the edge node. For example, we can detect that YouTube protocol is in place, and we can, for example, shape or block the protocol. So we can set up policies by inspecting the network traffic at the single edge nodes. So big thanks to Luca Deri, which is the main supporter of this n2n software. You can find here some links and n2n guide to the remote assistance. And this is all. Thank you for your attention.
Thank you, Emanuele. Are there any questions?
Hello, I have two questions.
Yes.
First of all, how it is possible to specify multiple supernode?
Yeah.
And the second one, if I have only one supernode and this go down, the node can able to talk directly, can continue to talk directly, or they have to wait that the supernode came up?
Okay. So, well, actually, the first answer is really simple. You just add different -L parameters, and you specify multiple supernodes. So it is OK. I did not mention that you can also set up the systemd services. So if you want a long lasting service, you can also set up the service with its own configuration file. For the second question, well, actually, the IP-based communication between the two hosts can still work. But since the layer 2 traffic still goes through the supernode, I think this should not work. So yeah, we want to improve the automatic detection of supernode state and maybe the migration automatically from one supernode to the other. This is something we are working on. OK. Thank you.
Okay. Anyone else? No? OK, so thank you again, Emanuele.
Thank you.